Welcome to the first lecture on process control, design, analysis and assessment. My name is Professor Raghunathan Rangaswamy and I am in the Department of Chemical Engineering at IIT Madras. The first few lectures I am going to make them very general, explain some important ideas in process control without introducing too much mathematics. And after these first few lectures, we will dive into the course in its real detail. Many of you might have seen the introduction video for the course. There we talked about the motivations for process control, and we said the field of process control deals with design of control systems for given processes. Basically, whenever we talk about process control, there are certain objectives that we want to satisfy. We want to run the process safely. We want to run the process in such a way there are no bad effects on the environment. We want to run our processes in such a way that the equipment that is used in these processes lasts for a long time. We want to produce as much material that is of interest as possible while maintaining safety, environmental regulations and equipment protection. And we do not want to just make lots of material, we want to make lots of useful material, which basically means we want to make material or products of high quality. All of this impact, of course, the profitability of whatever we are doing. And how do we do all of this for a process when there are things that are really not in the control of people running the process? So, for example, if you are running a process, whether it is going to rain today or tomorrow is not in your control, the temperature of the surroundings not in your control, the humidity is not in your control, and every process basically takes raw material and then does something with it and converts that into useful products. And in many cases, while you might ask for raw materials of certain quality, you cannot expect absolute quality. So, in terms of the quality of raw materials, things could be different. So, you have to take all of this into account and still be able to run your plant profitably without damaging the surrounding environment. So, process control is a very critical component for us to be able to do this. So, we might say if you want to ensure smooth and stable process behavior, we need process control. If we have to run the process very well even with disturbances occurring, then we need process control. This is an example, a very simple example, an engineering example, not necessarily chemical engineering or mechanical engineering. It is just a simple example that we see in day to day that I had used in my introduction video to explain process control. I am going to take again the same example to kind of introduce some terms that we will see again and again in this course. So, I talked about an activity that many of us have undertaken, which is drive a motorbike on a road, and we talked about this before. We might want to ride the motorbike at a certain speed, which we might say is what we want to have because that is where it is most fuel efficient, or it could be just that it is a personal preference. I talked about this already. So, you might want to really drive a little fast with the wind blowing on your face, or you might want to drive a little slow to take in the scenery surrounding you and so on. So, what we really want to control in this process is the speed of the bike and what we have to manipulate to control the speed. So, whenever I want to set the speed at some value, there has to be something that I can manipulate so that I can increase or decrease the speed as might be the case. So, the manipulated variable in this case is a throttle. So, we use the throttle, and then if you want to speed up, we increase the throttle. If you want to slow down, we shut down the throttle and so on. Now, imagine that you are driving on the road and let us say you are driving at a speed that you are very comfortable with. So, let us take this scenario and then ask the question as to why I might need control. So, the answer to this question is going to tell us there are two types of control that are very important, from control in processes and so on. The very first control is because of the following: you are driving at the speed you want. However, suddenly you see a vehicle in front of you at a distance, and what you want to really do is you want to overtake this vehicle because it is going at a slower speed than what you are going at. So, one thing that you might do is you might move to the other lane and then increase your speed till you overtake this vehicle and come back to your original lane and then go back to the speed that you are doing. So, here the change in the speed or the change in the control variable is something that you have desired and you want to make this change. Okay. So, this is one type of control. So, everything is going as per plan, the output is at its value, but suddenly you want to change the output to a new value. Now, there is another situation where let us say you are going on flat terrain and suddenly the road starts sloping up, in which case you are holding your throttle at the same point, but you are not attaining the same speed that you attained before. So, this is what we call as disturbances, which is the things that change the control variable from its set value, even though you are holding your manipulated variable at the same value. So, this is outside of your control, you cannot control the terrain of every road that you drive in. So, things that are outside of our control we call as disturbances. So, here variations in terrain, hills, etc. So, there is a distinct difference between these two control activities. In the first case, while everything was all right, I actually kind of wanted to increase the speed in anticipation of something. It might be in anticipation of vehicle ahead of me at quite a distance, or it could be in anticipation of better scenery going to show up. So, I am going to slow down and so on. So, this is something that I am interested in doing to change the control variable. The other case is where there are things that are outside of my control, which is changing automatically the control variable, and I want to do something about that. So, the first type of control is what I am going to call as regulatory control, which is the most important type of control that is usually done in process plants. So, this relates to actually disturbances and the control variable changing according to the disturbance, and then you do something with your manipulated variable to bring it back to its original value. So, if you take this picture here, so here we are plotting the output variable. Let us assume the set value for this output variable is given by this line, and if you look at the initial portion of the curve, the output is at the set value. Now, this is like driving on a flat terrain at a particular speed. At some point, let us say the speed increases or decreases. So, for example, if you have a slope, let us say the speed increases. Now, what you want to do is your aim is to be right at this set point, but because of a disturbance the output has changed. Now, regulatory control is one where the manipulated variable is changed in response to this disturbance, so that this control variable ultimately comes to its set point value. So, you might have a certain amount of time before the output variable comes to its set point value. Nonetheless, after a while the output comes to its set point value. So, this type of control which is in response to a disturbance is what is called regulatory control. Now, look at this picture here. This is different from the other picture. The difference is, in this picture the set point was always at the same value, but here up to here the output is at its set point value. Now, what you are doing is you are actually asking the set point to be moved to a new value, right. This is out of your own interest. There is no disturbance here which has changed the output, but it is you are asking for a new set point to be followed, in which case you want the manipulated variable to be able to make changes such that this output after a while starts following the set point. So, this type of control is called servo control, where we expect the controller to follow the set point where the set point is changing. So, you can see the difference between regulatory control and servo control. Now, these are two important concepts that we use in control quite often, and you can imagine several examples of this in real processes. Supposing you are producing several products in a chemical process, and each product is selling at certain price, and there is a certain amount of effort that it takes to make a certain mix of these products. Now, depending on the market demand, you would have some set point for all of these products. Now, everything is going great and you are producing these amounts. Let us assume at some point the market dynamics changes and a product which was not selling for very high cost suddenly starts selling for a higher cost. Then what you will do is you will try to change the mix of these products. So, you are going to make more of some and less of some. So, your original set points are going to change and you are going to try and follow new set points. So, this is servo control. In the same case, for example, you have certain quality of these products, and the quality of these products depend on what comes into the process. Let us say there is some change in what comes into the process, so that is like a disturbance, in which case you still want to maintain the same product quality as before, that is you want to reject this disturbance that comes through the input material, then this would be regulatory control. Now, we might ask question as to, if I have a model for this process, can I do this servo control and regulatory control? In other words, a simple question is, if you know there is a particular throttle position at which I can go at a certain velocity, then is it just a question of moving from one throttle position to another to be able to do this control? Is an important question to ask. Now, the answer to this question is, even if we have model for a process, we still require what I am going to call as feedback control. We will explain what this feedback control is. This is because whatever models that you come up with, a particular throttle position I will get a certain velocity, it is never perfect. Models are always beset with some error or the other. So, there is some uncertainty always associated with models. So, even if I am able to develop a model for how the control variable will behave with respect to a manipulated variable, you still need this notion of feedback control, which we will explain subsequently, for you to be able to efficiently do regulatory control and servo control. So, the questions are then, first is, since we talked about a model, how does one characterize the behavior of these processes using a model quantitatively? So, that is one question that we ask. And the second question that we ask is, how does one use this knowledge to design effective control systems? So, these are the two fundamental questions that actually we are going to answer through this course. Now, I want you to look at some of the words here. Just now when I was explaining the bike example, I said maybe we have a model where a particular throttle position gives you a velocity, right. So, that type of model is what we would call as a static model, where we say, okay, if I give you a throttle position, here is a velocity. So, that is like a static map. But in reality, when you are driving these bikes, what you are going to do is you are going to move your throttle from one position to another. And for all of us who have driven motorbikes, we know that if, let us say, I start my throttle and take it to full position, I do not get to the final velocity right away. So, it takes a while before that final velocity is reached. So, even though I have instantaneously changed my manipulated variable, the effect of that manipulated variable on the control variable is not instantaneous. It takes a little bit of time before this effect is seen in the control variable. So, that time aspect of the change of control variable, whenever there are changes in the manipulated variable, is what we call as a dynamic behavior of the process. So, this is an important concept from process control, and what we need to do is we need to be able to characterize this dynamic behavior of the process. Only if we characterize the dynamic behavior of the process would we be able to do good feedback control, as we will see as we go through this course. So, whenever there is a process, one of the questions that we need to answer is, how do I model this process quantitatively, the dynamics of the process, wherein we mean if I change a manipulated variable, how would it affect the control variable from a time behavior. And once we have such a model, the next question that we would be interested in is, how would I use such a model to design effective control systems. So, here is where we bring this notion of feedback control for the first time. I am going to stick to the same bike example for a few more slides to explain this concept of feedback control. This block diagram here is something that we will see several times through this course. So, let me start explaining this block diagram. Before I explain this block diagram, let us think about the feedback control that we actually do as humans when we ride a bike. So, let us assume you are riding a bike at a certain speed, and then there is a sudden incline, and then you start going over the incline, and then the speed comes down. At this point, the person driving the bike, who is the controller, basically senses that the speed has come down, and you could sense the speed has come down through just a physical means, or you could look at the odometer reading and then see that I was driving my bike at 60 kilometers per hour. Suddenly I am going down to 55, a little bit later I am going down to 50. And this change is because of a disturbance, which is an incline that has come up, and this is what we showed in the picture in the last slide. Now clearly you want to be at 60 kilometers per hour and you are sensing the speed is not at that level. So what you do is basically you say, look, there is a difference between where I want to be and where I am at, and that difference in some sense drives how much of manipulation I do. So for example, if it is a very slight incline, the speed has come down only a little, you will feel that there is only a little change in the field. So you might increase your throttle position by a little bit. However, if it is a very steep incline, your speed is really dropping, you are going to move your throttle to the other side very fast. So notice that as a human being, a controller here, you are looking at the difference between the control variable value that you want the control variable to have, which is what we are going to call as the set point, the value that the control variable should have, and the actual value that the control variable has. You see the difference, and that error drives your manipulation, right. And the controller here in this case is the human being, and the human being says, okay, it is very different from the speed that I want, so I am going to increase my accelerator or the throttle to a large amount, or if it is a smaller difference, smaller amount, and so on. So this concept, which we are very good at naturally, how do we translate to industrial systems, right? How do you think about the mathematics of this in industrial system? Remember, we do several activities in a feedback control in a very efficient way. Any game that you play, if you are playing tennis, there is feedback control all the time. So you know that there is a ball and your racket has to go and hit the ball, and you know the desired position is close to the ball, but if your racket is far away, then your legs move towards the position and so on. So there is very complicated feedback control that is happening there, which we do seamlessly and effortlessly. How do we bring those ideas to real processes is the key question that we are going to ask. And the word feedback is because the actions are taken based on the feedback, which is the error feedback, which is the difference between where I want to be and where I am actually at. So where I want to be is a set point, where I am actually at is the actual value. So when you start doing this mathematically, you start doing this simple block diagram. It will take us a while before you get comfortable with this diagram, because there is something called a disturbance model, there is something called a process block, controller block here and so on. However, there is only one bike here, right. So how do I connect this bike to these is important question, and the way we will do this is we will first talk about this block diagram and then tell you what these are, and as we go on to the modeling exercise, you will see how we think about these blocks and what are these and so on, and how do they come about to be in this form is something that we will describe as we go through this course. For now, let us look at this block diagram. Let us first understand what each of these elements mean. How do I translate this bike to these elements is the next question, but let us first understand what these elements mean, and then, as I said before, when we actually do modeling, we will see this again and again, so that you get very comfortable with this block diagram. So this block diagram basically says the following. So what you do is you start with each of these lines. So I will go through this and then explain this block diagram, and we will make more comments about how am I able to separate this process and disturbance as two blocks and so on later. So those are based on principles of linearity and so on, which we will come back to later in the course. So for every one of these lines in this diagram, so I can associate a variable. So for example, I am going to associate a variable u here, and this u is what is the manipulated variable that we have talked about quite a bit till now. So this is the manipulated variable. Now whenever there is a block, what it says is this manipulated variable goes through whatever is this process block, which is actually a mathematical block. We will come back to describing this later, and there is an output which comes out of this. So, an input goes and there is an output from the block. How this input is converted to the output is something that we will see later, but as far as we want to understand now, we will just say that this is the output y subscript p, and p stands for process here, and I will explain this subsequently. Similarly, if you look here, there is a d, which is the other word that we have been using, which is called disturbance, and when that goes to the disturbance model, you have what is called yd. Okay. So, every block has an input and an output. Okay. So, this block has u as the input, y subscript p as output, and this block has d as the input and y subscript d as the output. Now, whenever you have circles like this and signs like this, so basically what it says is this circle takes as many inputs as you can give it, in this case 2, and it tells you what you should do with these 2 inputs. So, in this case it says okay, there is one input here, there is one input here, add them up and that is output of the circle. So, here I am going to have yp plus yd, and this is going to be my total y. Okay. So, I will explain this with this bike. Let us hold on for some more time. Now, similar to this block, this is another circle and it has 2 inputs. So, one is this y. So, let us call this y set point. It says take the difference between this y set point and y, and then the output here is the error, which is going to be equal to y set point minus y, and this error is what goes as an input into the controller, and it is the same line. So, I have the same e here, and the output is u because it is the same line u. So, now you notice this controller takes the error as the input and then says what should be the manipulated variable, and clearly that is what we saw in the bike. So, I told you if I am going at, if I want to go at 60 kilometers per hour and I find that I am going only at 55 kilometers per hour, then there is an error of 5 kilometers per hour, which basically is what makes me move my throttle. So, that controller tells you what the output throttle position should be. So, you can understand this controller. In this example, this controller is really the human being that is driving the bike. Now, this looks a little more complicated. It says I have only one bike, but why do I have 2 blocks? So, you might want to think of this as this, right. So, both of these actually represent the bike. This block represents the effect of the throttle on the speed. Clearly y is the speed. So, what we want is just the speed. Now, this block represents the effect of the throttle on the speed. So, for example, if you increase the throttle, the speed will increase. If you decrease the throttle, the speed will decrease, and so on. But the speed of the bike, as we all know, does not depend only on the throttle. I could be in the same throttle position and I will be going at a certain speed on a flat road, and at the same throttle position, if the road is slightly inclined, I will be going at a lesser speed. So, just the throttle position alone cannot model the speed. The disturbance, in this case, for example, the incline of the road, if you think of that as a disturbance, that also dictates what the speed is. So, you might want to think of these as 2 effects that have a final impact on the speed, and since at the initial portion or for the large portion of this course we are going to talk about linear systems, whenever you have things that are affecting together, if it is a linear system, the total effect will be the sum of individual effects. So, for example, the speed mathematically we are saying is a combination of the effect of your throttle and the effect of your disturbance, so that you can actually model both incline and the throttle position on speed. So, that is the reason why we have this. Now, this is a critical circle because I am able to just add these 2 effects to find the speed, because I assume the process is linear. If the process is not linear, then this would not be a valid assumption. So, that is an important thing to understand. So, this is your basic feedback diagram where I show the output, a comparison with a set point, the error driving the controller, and the manipulated variable driving the process, and the disturbance also driving the process, and because it is a linear process, this y is a sum of yp plus yd. Okay. Now, if we think about this in little more detail, so for example, I want to just take this portion and then say, okay, here I have u which is going into a process and I get y as output. So, what does this mean? So, here is an example. So, this is your u and this is your process and this is your y, which we call as the process response curve. So, here in the schematic we show that if you suddenly increase your input by a certain amount, what is called a step change, how is your output going to vary? So, it might vary something like this. So, to get the model to say that if I change my input this way, the output will change this way is the mathematical model of the process. And you can see that this will be very consistent with this bike example. So, for example, if you are at a particular throttle position and you go to a new throttle position, the speed immediately does not change, the bike picks up and after a while it goes to steady speed, right. So, it was at this speed and then you change the throttle position. At the new throttle position, this is the final speed, but it takes a little while for the bike to pick up to go to the new position. So, this is what we talked about as the dynamics of the process. So, just because I change my manipulated variable instantly from here to here, my output does not go from here to here instantly. It takes a while for the output to go from its value to the new value, and this model is the dynamic model of the process. How do you mathematically write equations so that this dynamics is captured is something that we are going to see through this course, but I just wanted to give you the basic idea of how all of this thing work together. So, to summarize, there is a dynamic model for the throttle with respect to speed. Clearly, there is also a dynamic model for the speed with respect to incline. So, for example, if you are going on a flat road and there is a sudden incline, the speed does not go to a low value right away. So, it takes a while to go to the low value, and that is basically the dynamics of the disturbance. And because we assume that the underlying process itself is linear, which is just an assumption, we say that the total overall effect of the manipulated variable and the disturbance variable can be added together and represent the final output. Okay. So, there will be a dynamic model for the manipulated variable, there will be a dynamic model for the disturbance variable, and there will be a controller which is basically seeing the difference between the actual output value and the set point, and using that it is going to say how I manipulate my variables. Okay. So, in this course what we are going to see is we are going to see how to build this disturbance model, how to build this process model, and how to develop these controllers, so that whatever activity that we talked about here for this bike, we can take it to engineering systems and let computers do this control for us. Now, if you notice in the previous example, there is one manipulated variable which is a throttle position, and then there is one control variable which is a speed. But in real plants there will be multiple inputs and multiple outputs. So, as I mentioned before in the introduction video, we still need to think about how we will do this when I have multiple inputs and multiple outputs. How do these ideas translate to multiple inputs and multiple outputs? This is something that we are going to deal with in detail. So, what I will do is in the next lecture, I will talk about how we can think of this multiple input multiple output control from the viewpoint of single input single output control. This is because one of the general questions is that whenever you do an undergrad control class or undergrad material, almost about 75-80% of the time we typically talk about just CISO control. But we always know that in real industrial process it is not CISO control, it is going to be MIMO control. In fact, even in the bike example, if I complicate it a little bit more, I can think of two inputs. So, for example, the speed is not only based on your throttle, but it is also based on a brake that you apply. So, if you throttle and apply your brake at the same time, then the speed dynamics will be different from if I applied my brake alone or throttle alone. So, even in that simple example, there are more than one inputs that actually affect the output. So, when even for such simple examples it is MIMO control, for large complicated processes it is definitely going to be MIMO control. So, one question that can arise is why are we studying CISO control for about 75% of the course when really most processes are MIMO control? So, I will explain how this MIMO control problem is broken down into CISO control problems without losing much of the aspects of MIMO in very simple cases. And then of course, the second part of the course, as I mentioned before, we will really look at MIMO control in its entirety. So, that is an important aspect of control that we need to keep in mind. I also want to point out here, actually in most real processes such as the one that is shown here, in fact this MIMO control problem is largely addressed as multiple CISO control problems. There will still be many CISO loops in this facility which will be doing its job very well. So, we need to really understand how is this CISO control so universal, or it has such universality that it is able to work in about 90-95% of cases, even in real industrial systems where there are multiple input multiple output effects. So, that is something that we will talk about in the next lecture. So, I will come back in the next lecture and pick up from here and then explain how a MIMO control problem is broken down into several CISO control problems without losing the essence of the notion of MIMO control, and later we will see MIMO control completely as MIMO control itself. So, I hope this introduction set the tone for what is going to come in the future lectures. I will see you again in the next lecture. Thanks.